Hello students. In the last class, we talked about some of the colligative properties we talked about relative lowering in the vapor pressure, we talked about elevation in the boiling point, depression in the freezing point. Today we'll be adding one more colligative property to that is the osmotic pressure. In today's session, we'll be doing this colligative property. We'll be studying about osmotic pressure, what osmotic pressure basically means, the formula for osmotic pressure, and after that we'll be talking about abnormal molar mass. That is the last topic of this chapter. So first we'll see what does osmotic pressure means. Before starting with osmotic pressure, we'll talk about osmosis. What is osmosis? Osmosis, well, if I talk about osmosis, it is the movement of solvent particles from high concentration of solvent to low concentration, or we can say from low concentration region to high through a semi-permeable membrane. Well, here I would like to tell you that when I am saying the movement of particles from low concentration region to higher, that means low concentration of the solution. Inside there is high concentration, inside that semi-permeable membrane there is high concentration, and outside there is low concentration. That means I have got pure solvent. I'll explain you that with an example. Suppose I have got a container. This is the container I have got. In this container I have got an inverted funnel also, like this. And this funnel is fitted with a SPM, semi-permeable membrane. So on the mouth of this, I got a SPM, that is semi-permeable membrane. When we talk about semi-permeable membrane, it's a membrane that allows semi-permeability. That means the solvent particles can move only in one direction. They cannot move in both the directions. They can move only in one direction. Here in this funnel, there is some graduations like centimeters, millimeters, they are graduated here. And inside this funnel, I have got a solution of, say, sodium chloride in water. So this is the solution of sodium chloride in water I have got. This is NaCl plus H2O. Outside this funnel, I have got pure solvent, that is water. So what will happen? This water will start moving in. It will moving inside the solution. I'll show it with a different color. The solvent particles, they will start moving inside the solution. This movement is osmosis. So if we talk about the concentration of the solution, it is higher inside the funnel and it is lower outside. So the movement of solvent particles from lower concentration region to higher concentration region is known as osmosis. Now what will happen as osmosis will occur? The level of the column will increase. That means the level of the solution will increase. Suppose it has increased up to this level, and suppose this is x millimeters. It can be any value, x millimeters. But now the weight or the pressure of the solution has become so large that no more solvent particles can move in. This pressure is known as osmotic pressure. So osmotic pressure, we can say it is the minimum pressure. It is the minimum pressure exerted by a column to stop osmosis. It is the minimum pressure exerted by a column to stop osmosis. For example, if I put some grains into water, they will absorb water. The water will start moving inside the grain because the skin of the grain is semi-permeable. The water molecules, they'll move inside the grains, they will swell, but never you'll see that the grains are getting ruptured, because after a particular time the grains, they develop so much pressure inside that pressure prevents osmosis. So it is the pressure that develops inside the column which stops osmosis. When the pressure was lower than osmotic, suppose in this case this x millimeter is osmotic pressure, I'm marking it with pi. Now here we'll see that the osmotic pressure is pi and the pressure of the column is equal to pi. Suppose this pressure of the column, I'm marking it with P. If the pressure of the column becomes equal to osmotic pressure, then no more osmosis occurs. Such a solution is known as isotonic, isotonic solution. In such a solution, no osmosis will occur. However, when the pressure was lesser than osmotic, when P was lesser than pi, when the pressure of the column was lesser than osmotic, then osmosis was occurring. Such a solution is known as hypotonic, hypotonic solution. In such solution, osmosis occurs. Osmosis will take place. If the pressure of the column is more than osmotic, in that case, the solvent particles will start moving out. That means reverse osmosis will occur. Such a solution is known as hypertonic solution. So in that case, you will have hypertonic solution. So in this case, reverse osmosis, reverse osmosis will occur. Well, if we talk about the factors on which the osmotic pressure depends, we'll see that this osmotic pressure basically depends on the temperature and on the concentration. I'll give you one more example for that. Now, suppose we'll move back to the same column and we'll see. Suppose in this column, the osmosis has stopped when it has acquired a value of x millimeters of mercury. At that pressure, the osmosis has stopped. Now we'll see why this osmosis was actually occurring. This osmosis was occurring because of the difference in the concentration. There was a difference in the concentration of the solute between the solution and the solvent. That's why the osmosis was occurring. Now, this osmosis has stopped after reaching a value of x millimeters. That is the osmotic pressure. Now, in this case, suppose I add more sodium chloride into the solution. If I add more sodium chloride, again osmosis will occur. And now it may happen that it will move up and will reach a value of, say, y millimeters. So it shows that osmotic pressure is directly proportional to concentration. The higher the concentration, the more will be the osmotic pressure. Again, the osmotic pressure was occurring due to the difference in the concentration between the solution and the solvent. Now, if there is a large difference in the concentration, the osmotic pressure will be higher. So it is directly proportional to the concentration. The second thing is, osmotic pressure is also directly proportional to temperature. Now suppose in the first case, the osmosis had stopped after reaching a value of x millimeters. This is the osmotic pressure. Now what I am doing, I am providing some heat energy to the solvent particles. If I give some heat energy to the solvent particles, these particles will again get energized and they'll start moving in. They will move to such a place where they were not entering or where the pressure was enough to stop them. Now the pressure is not enough. We need more pressure to stop them. So more pressure is required and osmotic pressure will increase. So we can say osmotic pressure is directly proportional to the concentration and osmotic pressure is directly proportional to the temperature. That means osmotic pressure is directly proportional to concentration into temperature. That means osmotic pressure is proportional to number of mole per unit volume. This is what the concentration is. I'm talking about molarity into temperature. Or I can say pi V is equal to nRT, where you know R is a universal gas constant. So it is a universal gas constant. We'll use it here. So this is the formula for calculating osmotic pressure. Well, as far this colligative property is concerned, osmotic pressure, many a time, many theoretical questions or conceptual questions they are asked on this topic, like why it is considered to be the best colligative property. Well, osmotic pressure, unlike elevation in boiling point or depression in freezing point, osmotic pressure is measured at optimum temperature. Now, since it is measured at optimum temperature, neither the particle they undergoes dissociation, as in case of elevation in boiling point, or they undergo polymerization, as in case of depression in freezing point. So, number of particles does not changes. That's why through osmotic pressure, we can calculate accurate molar mass of an unknown solute. Whereas in case of elevation in boiling point or depression in freezing point, we get approximate molar mass, not accurate molar mass. Likewise, if we talk about relative lowering in the vapor pressure, relative lowering in vapor pressure is applicable only on high concentrations. If there is very little amount of solute in the solution, the relative lowering in the vapor pressure will happen to such a lesser extent that it is very difficult to measure. Whereas osmotic pressure is applicable even on dilute solutions. So this is the advantage of using osmotic pressure. You can calculate molar mass of polymers very accurately because it works at optimum temperature. So no dissociation, no association. Moreover, it gives accurate reading even on dilute solutions. Many time questions they are framed on the blood also. Like we talk about if we talk about blood, the concentration of blood is zero point 0.9 mass by volume. So as compared to the concentration of the blood, the cells inside the blood they are also placed like that. Means the pressure inside the cells, the white blood cells or the red blood cells or the platelet, it is in accordance to that. They are maintaining some osmotic pressure according to that, so that more solvent particle will not come out, and they have got a particular volume that is known as the cell volume. Now, what happens if the concentration of salt in the blood increases? If it becomes more than 0.9%, supposedly it becomes 1%. In that case, the concentration of the salt is more outside the cell. Now, the solvent present inside the cell will start moving out. Reverse osmosis will occur and the cell will shrink. On the other hand, if the concentration of the salt in the blood is lesser than zero point 0.9, in that case, more osmosis will occur and the cell will get swelled up. So this is what we observe in biosphere or in human blood also, where osmotic pressure very correctly maintains this volume of the cell. So this is all about osmosis, and as I told you, it is one of the very good and very acceptable, accurate colligative property. Now we'll move on to the next topic, that is abnormal molar mass. When we say abnormal molar mass, what does that means? Well, before that, I would like to tell you, or I would like to recap one more thing. This we did while starting colligative properties. That colligative properties are directly proportional to number of solute particles. Colligative properties are directly proportional to number of solute particles, and colligative properties they are inversely proportional to molar mass. That's why colligative properties they are used to calculate molar mass of an unknown solute. But many times what happens, the solute particles either they undergo dissociation or they undergo association. As a result of that, the number of solute particles changes. When the number of solute particles will change, the colligative property will also change. And when the colligative property will change, the molar mass which we will calculate will not be accurate. It will be different. It will be incorrect. We call it abnormal molar mass. I give you one example for that. We'll start with dissociation. So we'll see for dissociation. Suppose I'm talking about sodium chloride. If I talk about sodium chloride, suppose I have taken 1 mole of sodium chloride in a solution. On dissolving in the solvent, it will break up into Na positive and Cl negative. That means I took the concentration of the solute 1 mole but on dissolving in water, it has got converted to 2 moles. That means the number of particle has doubled. When the number of particle has doubled, the colligative property will also get doubled. And when the colligative property will get doubled, the molar mass which will calculate through it will be around half of the actual mass. Suppose the molar mass if we calculate the correct molar mass of sodium chloride is 58.5. Now, in this case, if I calculate the molar mass of sodium chloride through any of the colligative property, that is relative lowering in the vapor pressure, elevation in the boiling point, depression in the freezing point, or osmotic pressure, in that case, the pressure which the molar mass which I will observe will be around 58.5 by 2. That is nearly half because the number of molecules are getting doubled up. In that case, we need to correct it. And we can correct it like what I can write 58.5 by 2. If I multiply it by 2, I will get 58.5. That means if I multiply the observed molar mass with Van 't Hoff's factor, I will get correct molar mass. So I can say Van 't Hoff's factor is correct molar mass upon observed molar mass. This is in terms of molar mass that I can calculate Van 't Hoff's factor. I can also calculate this Van 't Hoff factor in terms of colligative property. I can write colligative property observed upon colligative property calculated. Well, I'll make this unclear to you. What does this means? See, correct molar mass is the molar mass that you have calculated. Here in this case, the correct molar mass is 58.5. Observed molar mass is the molar mass which you have got through a colligative property. That is relative lowering in the vapor pressure, elevation in the boiling point, depression in the freezing point, or osmotic pressure. That is observed molar mass. Likewise, observed colligative property. It is the property which is observed by someone who is posing a question to you. I give you one example for that. Suppose a question is given to you, 1 gram of sodium chloride when dissolved in 100 gram of water shows an elevation in boiling point of 1 degree Celsius. So this elevation in boiling point of 1 degree Celsius is observed by the observer. So this is the observed colligative property. We'll call it observed colligative property, which is given in the question. You'll not rely on that observed colligative property. You yourself will calculate again. You'll calculate that colligative property again by using the same formula, that is delta TB is equal to KB into molality. Now the colligative property which you are calculating through that formula is known as the calculated colligative property. So observed colligative property is the one which is given in the question. Calculated colligative property is the one which you are calculating. So through them you can calculate Van 't Hoff's factor. Well, Van 't Hoff factor, it helps in large number of things. Here in this case, Van 't Hoff factor will help you in calculating the degree of dissociation. In this case, I can easily calculate the degree of dissociation, that is alpha, that is equal to I minus 1 upon n minus 1, where alpha is degree of dissociation. I, you very well know, I is Van 't Hoff's factor, and n is the number of part in which the solute is breaking. Number of parts in which the solute is breaking. So this is how you can calculate degree of dissociation. Now we'll move ahead. If you will calculate Van 't Hoff's factor, after calculating Van 't Hoff factor, if you multiply a colligative property by Van 't Hoff factor, you will get the correct molar mass. As I told you in this case also, if you will multiply the observed molar mass by Van 't Hoff factor, you will get the correct molar mass. So here in this case, we can write P naught minus Ps upon P naught is equal to I into Ka. So that will give you the correct molar mass. Likewise, delta Tb is equal to I into Kb into molality, or delta Tf is equal to I into Kf into molality, or pi V is equal to I nRT. So if you multiply these colligative properties by Ventoff's factor, you will automatically get the correct molar mass. Although these colligative properties, they'll give you observed molar mass, but as soon you will multiply them by Ventoff's factor, you will get the correct molar mass. Now we'll talk about the second part, that is association. Association. Carboxylic acids are a very good example of this. If I got a carboxylic acid like RCOH, in water it will undergo dissociation to RCO negative plus H positive. But if I put a carboxylic acid in a non-polar solvent like benzene, it will undergo dimerization. It will form hydrogen bonding. In that case, I will observe intermolecular hydrogen bonding in carboxylic acid like this. Now, H is H positive in both the carboxylic acids and oxygen is negative in both the carboxylic acids. They will develop hydrogen bonding, due to which they will get attached. So generally they undergo dimerization. So suppose I got 2 moles of RCOH. They will undergo dimerization to give me RCOH whole twice. Here in this case, the value of N is 2. It is undergoing dimerization. If it is undergoing trimerization, it will become 3. Tetramerization, it will become 4. So the number of molecules which are undergoing association, that is actually N in this case. Now again in this case, suppose the molecular mass, the correct molecular mass of this carboxylic acid is X. This is the correct molar mass. When these carboxylic acid molecules they are undergoing association, their number of molecules are decreasing. They are becoming nearly half. When number of molecules are becoming nearly half, that means the colligative property is also becoming nearly half. When the colligative property is decreasing, the molar mass will increase. It will become really twice, means approximately twice of the actual molar mass. That means if the correct molar mass of this carboxylic acid is X, then the molar mass observed through a colligative property will be nearly 2x. In that case, the Ventoff's factor will be x upon 2x. That is 1 by 2. So from here it is clear that Ventoff's factor is more than 1 in dissociation and Ventoff's factor is lesser than 1 in association. In association it decreases. So here in this case you will observe that Ventoff factor is less than 1. By using this Ventoff factor we can calculate the degree of association. That is alpha is equal to 1 minus I into n upon n minus 1. Students, if it comes on to calculating Ventoff factor, again you will calculate in the same way. Van't factor as you calculated in dissociation, that is correct molar mass upon observed molar mass, or observed colligative property upon correct colligative property. This will give you Van't factor. And by using that Van't factor, you can easily calculate the degree of dissociation. Again, I'll give you one example for that. There's an example given in NCRT also, like 1 gram of a solute is dissolved in 1 gram of a carboxylic acid, benzoic acid, when dissolved in 20 grams of benzene, shows a depression in freezing point of say 1.3 Kelvin. The Kf for benzene is say 4.9. Any value, I'm giving these value randomly. Say it is 4.9. What is the value of Van't factor? Now, what we'll do, we know that the observer is showing a depression in freezing point of 1.3 Kelvin. That is the observed colligative property. Again, we'll write down the formula, that is delta Tf is equal to Kf into molarity. And I'll calculate delta Tf. Kf is already given me, like 4.9. Into weight of solute, that is 1 gram. Upon molar mass of solute, benzoic acid, that I'll write like 122. Into 1000 upon weight of solvent that is already given me 100 grams. From there I'll get the value of delta F. This delta TF which I'll get is the correct colligative property or the calculated colligative property which I am calculating. So I will write Van Taus factor is equal to observed colligative property, that is 1.3 Kelvin, which it has already stated, upon the one which I have calculated. So Van Taus factor is observed colligative property which is given in the question upon the colligative property which is calculated by you. That will give you Van Taus factor, and through that you can easily calculate the degree of dissociation. Again, in this formula, N stands for the number of molecules which are combining together. If two molecules they are combining together, then the value of N is 2. If 3, then it is 3. So it is like that. And this is how you can calculate the degree of association. This was the last topic of your chapter solutions. So with this chapter is over, and we'll be doing some questions based on this in our next lecture. Thank you very much.